Hello, in this video we're going to be talking about the standard model of particle physics. We're really just going to be doing an introduction to the standard model and the different elementary particles or fundamental particles. Really just going to go over what they are, how to find them in your data booklet, and understand kind of how we categorize them. All right, so what we're really looking at here is elementary particles, the smallest pieces that make anything up. We have a lot of different levels of this. We've talked about the atom, which is a very small thing that makes up all matter. But of course, we know the atom has a couple parts to it. We now know that there's a nucleus, a small, dense, positively charged thing in the center of the atom, and these electrons flying around it. And we know that the nucleus is made up of protons and neutrons, these other smaller particles. Turns out the electron is as small as we get, but protons and neutrons are made up of even smaller particles called quarks. And so we're going to be looking at these very smallest particles that make up stuff. Quarks, which make up protons and neutrons, and many other types of particles that are much less common, as well as the electron and some of electron-like things that are also much more rare. But so what we're looking at is called the standard model. And it turns out the science of describing how these particles interact and behave really can be used to describe almost everything in nature to a surprising amount of precision. They really very, very nicely, the rules for how these particles behave describes basically everything from electric fields to thermal physics. It really explains almost everything. It's the closest thing we have to a theory of everything. One universal theory that describes and predicts everything in physics, with a couple exceptions when we get to spacey sizes. The math of the standard model itself is certainly beyond what we're going to need to worry about in IB physics. There is a fun minute physics video which gives you a good overview of just kind of how it's used. They don't, get into any of this math itself, but how it's used in a little more detail that I'll link. That's a pretty good little description of how we use this standard model. All right, but for us, especially in how we're going to start with this video, is we're really just going to talk about the different elementary particles or fundamental particles of nature, which can really be classified into three-ish different families. We have leptons, we have quarks, and we have bosons. The names of these particles get very fun. Okay, so this is just a kind of overview. We're going to break down each one in detail, but there's a couple different types of quarks. There's a couple different types of leptons. Like the electron is a lepton, and it turns out there's others. So there's kind of 6 of each, quarks and leptons, that we'll get into, and those are the main things. There's also this other thing called bosons that we'll talk about. So where these come from, we see all these different particles. We're going to start looking throughout this unit at different ways that we see these less common particles. One of the first ways that we detected some of these other particles that weren't protons or neutrons or electrons, which we're used to, is with cosmic rays. We've talked about these a little bit as a source of background radiation. Well, cosmic rays are high energy gamma rays, usually, that are, or particles even, that are flying through space. And when they interact with the atmosphere, turns out they smash together and create all of these other particles in what's called a particle shower. And basically, when a cosmic ray comes into the atmosphere, it can, through a number of different interactions, make a whole bunch of little particles along the way. It smashes into something and makes 2 new particles, which can smash into something and make more particles, and we get all of these different particles coming off. Here's an example. So we detect these. We can detect neutrinos. We can detect these things called muons. Lots of different types of particles get created. So here's just an example of what this looks like. A cosmic ray comes in from the atmosphere, and we get these secondary rays, which have all these crazy particles. Now, these are gamma rays. That's not too crazy. There's an electron, there's a positron, an anti-electron, a gamma ray here, but we have all these other little particles that we've seen and find. These we use a pi for these things. They're called pions. We'll talk about them. These are neutrinos. These are muons, which are kind of like electrons, but much bigger. So there's all of these particles, like pions and muons, that you don't normally see when we talk about what makes up an atom, but they show up in high energy collisions in space, in the upper atmosphere, And we've been studying them a lot in particle accelerators when we smash particles together and really see what are all of these particles that happen um, when matter interacts, and we get a whole bunch of them. So we're going to look at the tiniest building blocks that make up all of these particles. So the first family is called leptons, and this is, you want to think of this as the electron family. So these are elementary particles officially that are unaffected by the strong force. Remember, the strong force acts inside the nucleus, so it's stuff that's like not neutrons and protons. They typically hang out outside of the nucleus then, and so we have 6 different leptons. We call, this is the first fun vocab term, the different types of particles, we call them flavors. So there are 6 flavors of lepton, which are as follows. We have the electron is the first, most basic flavor, if you like, of lepton. That one we're pretty familiar with. And there is an accompanying neutrino, the electron neutrino, which remember always happens in beta decay. So that's the neutrino that goes with the electron. There's another particle, though, that was in the particle shower picture called a muon. We use the Greek mu for it, and this is very similar to an electron. It's negatively charged. It's not affected by the strong force, but it's much bigger than the electron. And then we have an even bigger one called the tau particle. And each of these has an accompanying neutrino. So each of these particles, the leptons all have a negative charge. The neutrinos have no charge at all. So I have 3 of these particles, 3 very low mass neutrinos, and there will be 6 anti-versions of these. Remember, an antiparticle just means the charge is opposite. So an anti-electron is a positron. It's identical to an electron in every way except it has a positive charge. So here's an overview of leptons, and here's what's in your data booklet. So this is what you have as a reference. You don't need to memorize a whole lot, which is the good news. This kind of tells you what you need to know. It shows you the 6 leptons, the electron and its neutrino, the muon and its neutrino, and the tau particle and its neutrino. So here's one picture, a chart to show those. The charge of all of the regular particles is -1. The charge of the antiparticles is +1. And because the neutrinos are neutral, the antineutrinos are also neutral. There's something called the lepton number, which we'll get into as we go through the unit. But those are the different particles, the leptons. They have nothing to do with protons and neutrons and quarks. They're their own thing. They're their own family. The mu and the tau are bigger cousins of the electron, is basically how you want to think of it. All right, and there's another class of particles made up of quarks. All right, there are 6 quarks, and this is the really fun one. They decided to name the quarks up, down, strange, charm, bottom, and top. There you go. Those are the 6 different quarks that make up everything, including protons and neutrons. So we use, little u for up, little d for down, little s for strange, and so on. The charges of these are kind of funky, but you'll see when they combine how it kind of works out. I wouldn't worry about this too much right now. Again, it's in your data booklet, so we'll look at how it's summarized. But I have these 6 different very little particles called quarks that will combine to make bigger things like protons and neutrons and all kinds of other particles. But these 6 quarks and the 6 leptons we just looked at make up all matter. The bosons are kind of an interactive particle that we'll get into. So here's how it shows up in your data booklet. We have the 6 quarks here. They tell you the charge of each one. So 3 of these quarks have a charge of 2/3 the elementary charge, and 3 of them have a charge of -1/3 the elementary charge, which is interesting. All right, but these quarks, we'll get into this as well, but you never see them on their own in nature, but they do combine to make bigger particles. So another kind of category name for you here, we call groups of quarks hadrons. A particle made of quarks is a hadron. So a proton and neutron are hadrons. We further split that up into a couple different things. So we have baryons are particles made of 3 quarks, and since they're made of quarks, they're hadrons. So baryons are hadrons that have 3 quarks. For example, the proton. The proton is a particle made of an up quark and an up quark and a down quark. Those three together combine to create a proton. So if you could look inside of a proton, you would see three smaller particles, two up quarks and a down quark. And their charge, if you believe it, adds up to +1e. You could also make an antiproton with an anti-up, anti-up, anti-down, and then you would have, looks exactly like a proton, except it's got a negative charge. You see here, there's a whole bunch of other ones. There's the neutron, of course, but then there's like a lambda particle, an omega particle. There are hundreds and hundreds of particles made of quarks. There's lots of combinations we can make. So, of course, the proton and neutron are the most common, but there's literally hundreds of these particles. The only thing you do need to memorize is the quark content of the proton and neutron. One is up, up, down. One is up, down, down. So those two things you'll have to memorize. Everything else will always be given to you. All right, and there's another class of hadrons. So again, hadrons are things made of quarks. If you have three quarks, you're a baryon. There's also these things like those pions, those pi particles, are mesons. They're made of a quark and an antiquark. So an up and an anti-down quark, turns out, combine to make this positive pion. All right, lots of particles like this. Again, we'll practice with these and get into them, but that's kind of the categorization. Here's a picture for you. The proton you can now picture as a particle made of three smaller particles, two ups and a down. The neutron made of an up and two downs. Those are the quarks that make up each thing. All right, so this is something I would encourage you to make a sketch of to help you kind of organize these thoughts. So the different types of fundamental particles then, we have leptons, which we started with, which is electrons, muons and tau particles, which are, this kind of separate family. They're not affected by the strong force. They're kind of their own thing. Then we have stuff made of quarks, which we call hadrons, and there's two types. There's a meson, which is a quark and an antiquark, or there's a baryon, which is made of three. And this is where like protons and neutrons are. Then there's bosons. There's gauge bosons and the Higgs boson. That's something we'll also get into further as we go. They're sort of how these particles interact with each other in a very broadly speaking way. All right, so what you really want to be able to do at this point is just kind of decode the data booklet, where these 6 quarks are and what you can read about them, where the 6 leptons are and what you can read about them. We will do a lot of practice with them as we go. Here's one more to give you a picture of the overview. So here's the different quarks. You can see they all have different masses too, very different masses. Some are much bigger than others. They have different charges. We in the IB don't worry too much about the spin thing. But here goes as well. The leptons, the electron, we know 0.511 is its mass in MeV per c squared. We have the muon, which is like an electron, but much bigger, right? A couple hundred times bigger, still with a charge of -1. And then we have the tau particle, which is even way bigger than that. So there's some very big particles, again, speaking in particle terms, each with an accompanying neutrino. There's the old charm quark, the strange quark. All right, so 6 quarks, 6 leptons. There's an anti-version of each. And then over here, we have the bosons, which we will be getting into. But for right now, we're really focusing on categorizing these different things. All right, so those are the particles of the standard model, just to give you a background on some of these crazy vocab terms are going to start throwing around. Like anything, it'll take some practice before you start getting used to the idea of charm quarks and strange quarks and hadrons and mesons, but it's all just vocab right now. All right, so try and organize those somehow, and they will help you going forward as we make our way through particle physics.